A third method of analyzing our transfer function is the use of a root locus plot. Assuming we have the following block diagram, we need to plot the root locus of the closed loop system for k greater than or equal to 0. We can manipulate this block diagram to simplify it down. First, we notice that we have a cascade arrangement of blocks, meaning we can multiply them together and combine them into a single block. Next, we notice a feedback arrangement, which can be simplified to the form of g of s over 1 plus g of s. Simplifying this expression further, we get the transfer function of the system. From this, we can obtain our characteristic polynomial, which is simply the denominator of our transfer function, where we have d of s, the denominator of the open loop, or any expression not related to k in the equation, and n of s, the numerator of the open loop, or any expression directly multiplied by k in the equation. Step 1 involves finding poles and zeros of the closed loop system. The 0 is found from n of s. We have a single 0 at -10. The poles are found from d of s. We have a pole at 0, and a complex pair of poles at -3/2 plus or minus 6.9j, found using the quadratic formula. Let's plot these on the s-plane. An important metric to note here is the number of zeros, m, which equals 1, and the number of poles, n, which equals 3. From this we obtain the value of n minus m, which in this case is 2. This value is used throughout the creation of the root locus, so let's keep it to the side here. Next, we are going to locate the centroid and asymptotes of the root locus. The formula for the location of the centroid is seen here. We take the sum of our poles, subtract the sum of our zeros, and divide by the term n minus m. So n minus m is equal to 2. We substitute our 3 poles, with one of them having a value of 0. We substitute our single 0, and after some simplification we find the location of the centroid to be at 3.5. Now the centroid is the location where the asymptotes of the root locus originate from. Having found the centroid, now we need to identify the angle of each asymptote. This is given by the following formula, where pi represents 180 degrees, and k ranges in value from 0 all the way up to a value of n minus m minus 1. In our case, k ranges from 0 to 1, where n minus m is equal to 2. At a value of k equals 0, we get an angle of 90 degrees. At a value of k equals 1, we get an angle of 270 degrees. Let's plot this information. The centroid is located at 3.5 and 0. The asymptotes are straight lines that originate at the centroid with angles of 270 degrees and 90 degrees relative to the positive horizontal axis. In the next step, we apply the no, yes, no rule. This rule states that for any point on the real axis, the root locus exists at this point if there are an odd number of poles and zeros to the right of that point. This rule applies only to the case of the root locus where the range of k is greater than or equal to 0. So starting from the absolute right side of our plot, we see that the portion from positive infinity to 0 has no poles or zeros to the right of it, meaning our root locus does not exist here. The next portion, between 0 and -1.5, has a single pole to the right of it. This is an odd number, and as such, the root locus exists on this portion of the real axis. Next, from -1.5 to -10, there are 3 poles to the right of the region. This is an odd number, and as such, the root locus exists here on the real axis as well. Finally, from the region of -10 to -infinity, we have a total of 4 poles and zeros to the right of the region, which is an even number. This means the root locus does not exist on this region of the real axis. We can draw the root locus on the real axis where it does exist with a pink line. The root locus for range of k greater than or equal to 0 always travels from a pole to a 0. Knowing this, we can indicate the direction of this branch of the root locus. Next, we must look for any breakaway or break-in points that exist on the root locus. This involves solving the following equation. The derivative of n of s multiplied by d of s minus n of s multiplied by the derivative of d of s, and we set it equal to 0. Subbing in the relevant values and simplifying the equation brings us to this final expression. Finding the roots of the equation returns the following values. Let's check if these points are valid candidates for being breakaway points. In the case of S1 equal to -15.604, we can plot it and see that our root locus does not actually exist at this point on the real axis. This means S1 is not a valid breakaway point and can be ignored. S2 and 3 are complex pairs and could potentially be valid breakaway points. In order to verify, we can obtain the value of k at S2 and check if it is consistent. The value of k at a given value of s can be obtained using the following expression. K is equal to negative d of S2 over n of S2. After substituting and simplifying the resulting expression, we see that we get a complex value for k. K is a real number, it cannot have an imaginary component. As S2 and S3 are complex pairs, we would come to the same conclusion for S3. Therefore, both these points are not valid breakpoints. This leads to the conclusion that we do not have any breakpoints in this root locus, for the range of k being greater than or equal to 0. Now we can look for angles of departure for the root locus. In the case of a root locus with a range of k greater than or equal to 0, the angle of departure represents the angle at which the root locus departs from each pole, and the angle of arrival represents the angle at which the root locus arrives at each 0. The angle of departure at pole n is given by this formula. The sum of angles from all the zeros to pole n minus the sum of angles from all the poles to pole n minus the term pi times 1 plus 2k, where k is selected to ensure that the angle of departure lies between negative and positive 180 degrees. For the next few seconds, we will simply substitute relevant values and simplify the resulting expression to obtain angles of departure at each pole. The angle of departure at pole 1 is found to be negative 180. The angle of departure at pole 2 is found to be 26 degrees, and the angle of departure at pole 3 is a negative of the angle of departure at pole 2 due to the symmetry of the root locus about the horizontal axis. This value is negative 26 degrees. We can visualize all these angles on the plot itself. For pole 1, we can see the root locus line departing at negative 180 degrees. The root locus departs pole 2 at an angle of 26 degrees and approaches the vertical asymptote. The root locus departs pole 3 at an angle of negative 26 degrees and approaches the other vertical asymptote. The angle of arrival at 0n is given by the following formula. The negative sum of angles from all the zeros to 0n plus the sum of all angles from all the poles to 0n plus the term pi times 1 plus 2k, where k is selected to ensure that the angle of arrival lies between negative and positive 180 degrees. Substituting relevant values and simplifying, we find the angle of arrival at 0,1 is found to be 0 degrees. This can be seen on the plot, showing the pink root locus arrival at the 0 at an angle of 0 degrees with respect to the horizontal. This concludes the creation of our root locus with a range of k being greater than or equal to 0. Something to mention here is that we did not create the root locus where the range of k is less than or equal to 0. This is commonly referred to as the complementary root locus of the system. I wanted to highlight that while the process of drawing the complementary root locus is very similar to the process we just followed, the rules and formulas used can actually differ, so make sure to use the right type of formulas and rules for each root locus plot. Now, before tackling the next question, it is important to mention what a root locus plot represents. A root locus plot is meant to show how the location of the closed loop poles of a system change as the value of k is changed. On a root locus plot, when k is equal to 0, the plot starts at the poles. The resulting root locus plot shows how the location of the poles change as k approaches infinity. This means that in each root locus plot, there are only as many branches as there are poles. The branch of each root locus departs at a pole and either arrives at a pairing 0 or simply approaches an asymptote as k increases to infinity. This means that on a root locus, the value of k is infinity at a 0. This also means that when the root locus crosses over to the right half plane, the system becomes unstable at that point. Keeping this in mind, let's move on to the next question. Here we are asked to find the value of k when the root locus crosses the imaginary axis. This is the same as asking for the upper range of stability for k. When our root locus crosses the imaginary axis, it is at this value of k when the system goes from being stable to unstable. Since we know that the value of k at the poles is 0, we are effectively looking for the upper bound of stability for k. This can be done using a Routh table. We begin by obtaining our characteristic polynomial. The d of s term denotes the denominator of our open loop transfer function, and the kn of s term denotes the numerator of our open loop transfer function. We can simplify this term to obtain an ordered polynomial. We can fill in the first two rows of our table by using the characteristic polynomial. We have a3, the coefficient in front of the s to the 3 term. Similarly, a2 is the coefficient in front of the s to the 2 term, and so on. This completes our first two rows. We can now move on to filling the rest of the table. For b1, we multiply a2 with a1 and subtract a3 times a0. This is all divided by a2. Substituting the relevant values, we get b1 is equal to 150 minus 7k over 3. b2 is simply 0 because the third column of our table is empty. For c1, we use the same procedure to obtain a final value of 10k. c2 is simply 0 because the third column of our table is empty. For stability, we require no sign changes in the first non-trivial column of the Routh table, indicated by the arrow. This means either all the terms in this column must be negative, or they must all be positive. As 1 and 3 are already positive, for stability we require that b1 and c1 are both positive as well. b1 is positive for k less than 21.43, and c1 is positive for k greater than 0. The upper limit of k here, 21.43, represents the value of k as a root locus crosses the imaginary axis. Having found this value, we can also ask, what is the value of s when the root locus crosses the imaginary axis? We can see that our root locus departs poles 2 and 3 and crosses the imaginary axis. However, we don't know the value of s at which this occurs. We can find this value by getting our characteristic equation and setting it equal to 0. From the previous question, we know that the value of k at the imaginary axis intersection is 21.43. We can substitute this value in and solve for s. The resulting polynomial simplifies to this expression. The first root we find is s1 equal to negative 3. We know this cannot be the correct value, as at the imaginary axis intersection, the value of s must be imaginary, with no real component. We get s2 equal to 8.45j, which satisfies the requirement of our solution having only an imaginary component, and we get s3 equal to negative 8.45j, which also satisfies this requirement. s2 is the upper value of s at the imaginary axis intersection, which we can place on the plot, and s3 is the lower value of s at the imaginary axis intersection, which we can also place on the plot. And that concludes this question. Moving on to the final question, we are asked to find the value of k at some arbitrary value of s equal to negative 5. Here we can use the magnitude condition with the following expression: k equals the product of the magnitude of s minus each pole of our system, divided by the product of the magnitude of s minus each zero of our system. Substituting and simplifying, we find the value of k to be 59.86. That concludes this tutorial, and I wish you the best of luck with your journey in control systems.